And I'm really happy that it's such a privilege to be first up. So let's just see how this goes. I'm going to share my screen.
Sorry, Kevin, I think there was a problem. I unfortunately did not start the event properly. So just to recap, we were just I did my introduction before we started the session fully. So I will just quickly, briefly redo the introduction. So thanks everybody for being here. This is the first of a series of sessions my collaborators and I organized to learn some methods for a research project we're doing. We got funding from the British Academy and support from the Institute for Lifecourse Development at the University of Greenwich for bringing a few speakers to campus for development workshops. But we expanded this to online sessions because there's a variety of methods that we'd like to showcase, and we figured why not. And I hope the series is a successful test of mutualist approaches to doing this kind of work, helping me in my research and you in yours, enriching the research area and broadening the networks generally. I thank every speaker who's offered their time and effort to this series. Today's speakers are Kevin Durrheim, a distinguished professor in psychology at the University of Johannesburg and head of the UJ Methods Lab, which promotes open access to open science in Africa, and Nnaemeka Ohamadike, an applied data scientist also at the University of Johannesburg, specializing in computational methods for detecting bias in South African news, and a senior data analyst and researcher at Good Governance Africa. In terms of the structure of the session, Kevin will give a conceptual overview for 30 minutes. Then we'll have a short question period for questions. Then Nnaemeka will showcase a technical demonstration for about 40 minutes. Please type your questions in the Q&A, or if using an older browser, in the chat, because Q&A won't be available. Kevin and Nnaemeka will attempt to answer as many of these questions as they can after their presentations. And if we have time at the very end, I'll call on a few people if they raise their hands to ask questions on screen. Today's session has automated captioning in multiple languages. If you're more comfortable in a language other than English, simply turn on the captions and change the language setting on the top right of the captions bar to your preferred language if available. The session will be recorded and uploaded to YouTube and our archives, and I'll provide the links at the end. So sorry again, Kevin, the floor is yours.
Okay, well, this is the second take at starting, and I'm really sorry if you missed the first take of Fo's introduction, because it's much more leisurely, and there was a moment of silence for the brutality in the world around us, and I'm sorry we didn't all share that together. So I just want to also start by congratulating Ford on getting this funding and making this happen. My work at the UJ Methods Lab is focused on using internet technology, exactly what we're doing now, to connect Africa to Africa, and just to have this portal into the global south as well is just fantastic. And of course, methods are critical because they're points of convergence in interaction, in thinking, in investigation. I'm going to talk a little bit about in this lecture. I'm not sharing. Let me share my screen. Here we are. So I'm talking about word embedding methods. So these are machine learning methods for understanding language. Of course, these machine learning models of languages, large language models, are all around us today in generative AI. I'm going to be talking about a very primitive algorithm called the word-to-vec algorithm. Nnaemeka will show us how to use it later on. And I've been working with this for about 3 years now, and I'm just learned so much about measurement in political psychology. And I'd like to share some of that with you about measuring bias, because bias is fundamental to what we are interested in. It's fundamental to all these inequalities that we're dealing with, all this brutality in the world around us. At the heart of it is our representation, our understanding of each other and how we should act in the world. And the tools that we have at our disposal are pretty primitive. If you think of Likert scaling and semantic differentials, these are almost a century old. And they have limitations. Here's an example of how we measure bias with the semantic differential scale. So this assumes that the bias is inside the person. The bias is in the person's head, and then each individual gets a score, and they're all, all the humans in your sample are ranked from the least bias to the most bias. So there's a model there of how bias exists. It's in people. It makes a whole lot of assumptions about symmetry, for example. The more you at the positive end of the scale, the further you are from the negative end of the scale, with the neutral in the middle. I mean, does bias have that kind of symmetrical structure? It's imposed on the world through the measurement tool. And this has become quite evident to us now because of the advent of machine learning and the proliferation of machine learning models in our society. So we've got these things now called algorithmic biases. So, which are defined here as just a Wikipedia definition. They're repeatable errors that privilege some at the expense of others. In job outcomes, in searching. I mean, we all experience bias, and we're on the internet all the time. That bias is there. It's outside of us. It's not only inside of us. We don't have to measure individuals. We're swimming in a sea of bias. It's all around us. And I did the search. I think I did last year. I looked for just to type in the word Asian girls it was a Google search engine. And you see that the search engine delivers a certain genre or a certain character or kind of response. Now, of course, Google is very well aware of a bias. It's a very powerful and rich company, and it's spent a lot of money trying to get rid of bias in their models. And yet, to this day, it's impossible for them to get rid of the biases. They're there. They're around us. They're all the time. Here's another example from DALL-E. So this is from a generative AI model. This is search for lawyer, and there's for flight attendant. So once again, you can see there's gender biases in what it delivers. Now, the question is, where do these biases come from? Well, they come from us, because we are using the internet to do certain kinds of things. Certain categories of people are looking for Asian girls, and they are satisfied with some kinds of images and not others. When people are uploading pictures of lawyers and flight attendants, they're uploading a particular genre of these things. So the biases actually come from us. And what these machine learning models do is that they become very, very well adept at absorbing the biases out of our practices, out of our culture, out of our existence, and then representing them back to us. Of course, there's a vicious circle in which there's ethical things here about these algorithms, generative AI, and how they sort of then start reinforcing these biases. But actually, at the end of at the start of it, they actually come from us, how we treat them. Now, computer scientists is most of this work has been done in I can call it computational science. Physicists, computer scientists, mathematicians, all sorts of folks are studying this. Yeah, their primary objective is to try and get rid of biases, to de-bias algorithms, for obvious reasons. Their political, ethical, economic. There's a whole lot of reasons why you'd want to de-bias them. As I said earlier on, and many others have said, it's not really easy to de-bias these things. But for us as social scientists, as political psychologists, we're actually interested in the biases, in studying the biases, because they're our biases, in studying how people use them, generate them, orientate to them, articulate themselves against them in this world, this environment of biases. So we need a way of externalizing or making these biases evident to us, so we can use them to study the way we produce them. So in other words, it's a social science of algorithmic bias. And so this is the model that we're using. It's a word embedding model, and I want to talk a little bit about in this just one or two slides here about what is a word embedding. And how they're trained, how do we get them? So a word embedding is essentially a sort of a representation of words as vectors in a multidimensional space. That's And there's an example of the output. So you input into this model text, natural language text, that's called natural language processing, natural language models, large language models. So you put in natural language, what people are saying, and it outputs, the algorithm outputs a quantitative model, which is a vector model of words. So, for example, in the example I've got over there, this was around, we've done quite a bit of research on anti-vaccination debate around COVID-19 in South Africa and in the United States. You put in tweets. Many people did not receive the booster, were killed by the pandemic. Let's stop the pandemic. Hashtag vaccines work for all, etc., etc. You put in, a million tweets, hundreds of thousands of tweets, whatever. Big data. It needs lots of data to create your models. And then basically what it does is it gives you a vector. Each word is represented by a vector, and a vector has got, that's a word vector. So you've got the word at the beginning, and then you've got a string of numbers which define an address for that word in a vector space. So that's the embedding. The embedding is the whole space, and each word has its place in that space. Now, when I talk about space over here, it's a very abstract space, because we us humans are very adept at thinking about a two-dimensional space and a three-dimensional space and maybe a four-dimensional space, but a 250-dimensional space is just mind-boggling. Or like these ChatGPT, millions of dimensions. They've got so much information in them. So that's what we mean by multi-dimensional space. It's a space where each word is located. So and that's why we call them word embeddings, because the words are embedded against each other in the space. I hope that's clear. If you've got any questions, I'm going to put on the chat all the question and answer. You're welcome to stick up questions, and I will try and answer them as we go along, and I might ask you questions as well. Okay, so there we are. So this is basically how these things work. What I've got over there is a representation. So instead of 250 dimensions, I'm just reducing it down for our minds over here to a three-dimensional space, which is a sphere. Okay. So how these algorithms work, and it's a very simple little text recognition problem that they solve. It reads all the text, word by word, as we would read the text in little windows, 10 word windows. So it goes through the words. For example, if you want to get something, it's trying to guess what is the next word. So it's text recognition, and it's creating guesses. If you want to get, then no to vaccines. So it's trying to guess the correct word that's going to go into that space, and it does it for all the words in all the language in these little windows. So it's a little window that reads the whole lot of the language, or the millions of tweets that you give it, and each time it's trying to predict the next word, and it gets better and better and better and better and better at predicting the next word using a neural network as its basic architecture at the bottom, underlying it. At the end, it's this numerical representation, in other words, the intelligence that it's developed to guess these words, and it guesses them very accurately. I mean, if you've used ChatGPT or any of these other chatbots, it's uncanny how well they can have a conversation with you about just about any topic you like, because they're very good at guessing words. So then in this three-dimensional model over here, each word in the language is represented on a sphere. It's a standardized or normalized vector. So in other words, each vector is the length 1, so it's a complete sphere, and every word is located somewhere on the top of on the surface of that sphere. That there is basically what a word embedding is. It's got all your language, the words in your language, represented by vectors, which give them an address or a place where they're located vis-a-vis each other in that multi-dimensional space. In this way, we've got a three-dimensional space. And of course, over here, it's very easy for, if you want to get COVID or if you want to get killed, are two candidate words that would work very well in that example that I've got over there. And hence, those two words are embedded quite close together in the embedding. The word that's not there, for example, is, let's just say bread is a word that is unlikely ever to be used in that sentence, and it would be nowhere near a COVID and killed. So words that are unlikely to be used in that context are embedded far away, and words that are almost synonymous with each other are embedded close together. That's basically how the word embedding works. Now, this is interesting. When I started working in this area, before I was interested in reading Wittgenstein. I was like sort of sort of an anti-mentalist. Psychology is where my philosophical background. And Wittgenstein always says that the meaning of words, there's these arguments about language games, is in their use. The meaning of words isn't, it's not, the meaning doesn't come out of mind. It comes out of the use of things. This is how we learn and how we teach others the meaning of words and concepts. We teach others how to use words. And basically, this is what the word embedding model does. It shows how words are used in natural language. And I think that's very, very important. That's why they absorb our intelligence, because what our intelligence is how we use words in natural language, because that's the meaning of the words. The meaning of the words is how we use them. How do we use the words male and female, men, woman, black, white, racial categories? How do we use them? How do we talk about people with different names, for example? And yeah, we have a metric now. The closeness of words to each other in an embedding is the metric, the basic metric of bias in meaning. Okay. So, and this is quantifiable. Nnaemeka is going to show us a little bit later on how to do some of these computations, but I'm just dealing here with what conceptually what we use as our measure. We use a similarity score. And a similarity score is essentially the angle between two vectors. In other words, are the vectors close to each other or are they far apart? When the vectors are close to each other, almost in the exact same direction, they're located next door neighbors, very close to each other, the similarity is 1 or very close to 1. And when they're at 90 degrees from each other, they're unrelated to each other. And then at -1, they have opposite meaning. So it's almost like a correlation coefficient, what we understand like a correlation coefficient. But the angle between the two vectors, which we call the similarity index, is the word similarity is our measure here of bias, or we can think of it as a kind of synonym that one word can be used interchangeably with another. Like COVID and apple can't be used interchangeably. They at 90 degrees to each other, but COVID and killed could almost. So you can see now the cultural understanding of linking COVID to death is represented in the way people have used those words in our language. Okay, so now we can do other kinds of things. We can create, and Nnaemeka, I think, is also going to show you how to do this. We can create dimensions. Like, for example, we can create female bias and male bias. And we just take a whole lot of female words and a whole lot of male words, and we just calculate the centroid of those words. And then now we've got the center, almost as it were, of female bias and the center of male bias. So we know where male and female bias are in this embedding. No questions yet. If you've got any questions, let me know, because it's quite technical. Okay, I'm happy to carry on.
We do have some questions if you'd like to take them now, but we can do this after. So the first question is, how much data do you need for this approach?
Okay, you need a lot of data generally, but there are shorthands, ways where you can pre-train an embedding and then post-train it again on small amounts of data. That's a quick answer. I'm going to give quick answers here.
Okay, and another question is, how does this take into account the context around the word embedding, like replying to a tweet or a parody, denying or criticizing?
So the algorithm that we're using over here, Word2Vec, doesn't take context into account. It just gives a single representation for each word. We find there's lots of advantage to that. We're still working on developing context embedding. It's called, rather than using the Word2Vec, we'll use the BERT embedding model. Much more complicated. And I mean, this can get extremely complicated with these transformer models, but the simple ones, and one thing I've learned from working with these physicists is simple is better. I think that these simple ones show us something about our own very simple heuristics in the way of navigating this field. So it's both of those are very good questions. There's lots of work to be done. We're just scraping the surface of this. Any other questions, Freud?
No, not that I can see.
Okay, that's fine. I'll carry on and then we can come back. If you've got any questions as I'm going along, just let me know and I'll keep the question and answer on my screen so I can
We
answer
have
them.
one more. What about a word which is the same but with two separate meanings, such as sick to mean ill or to mean cool? Can this
Yes,
confuse things?
yeah, so that currently with our model, we don't do that, like mouse and mouse, the mouse, the rodent, and mouse, the computer tool. Currently, we only have one embedding for mouse, but I mean, if you talk, if you've got your text is around computer scientists talking, we know what mouse means, but if your text is around sort of biologist talking, has got a different meaning. So we can a lot of the work is done in sampling, but the method that I'm going to be presenting today, only it's a simple embedding. It's a very old embedding. It's 2013 it was developed. It's a non-context sensitive embedding, so it gives one representation per word. I think that as I'll show, as you'll go through this, and as Nnaemeka will show you later, it's still a very, very powerful tool. The complex ones, the complexity, what we're going to get from the complexity is still work to be done. Okay, let's hold on a section there while I carry on a little bit. Okay, so now we've we've got all these male terms: man, boy, his, uncle, he; female words: woman, her, auntie, girl, she. We create the centroid. The centroid is basically like a mean of all these vectors. The mean vector is the centroid. So we've got now male bias and female bias within the embedding. What we can then do is we can then subtract the male bias from the female bias. Because why we subtract them is to create what we call a gender dimension, which is a direction in an embedding. And the reason we do that, because if males and females are actually embedded very close together to each other in the embedding, because they're human beings, they're used in so many similar ways, they're not spoken about with food, and so men and women are actually embedded very close together. So when we subtract the one centroid from the other, we take out what they share in common, just leaving their difference. And so that difference is now a direction that runs through the whole embedding that captures the whole of gender bias. And we can use this now, almost like the semantic differential between male and female, or positive and negative. We can create a positive and negative dimension. We can create a black versus white, a racial dimension. We can create an insect versus flower, to use the IAT kind of thing dimension. So we can create an infinite amount of dimensions. Inside, we can identify these dimensions inside, which are biases inside the embedding. All these biases somehow are related to each other as well. Okay. And here's what it looks like when we actually do something like this. Is Nnaemeka's work, actually. These are race stereotypes in a South African word embedding. And this is news around vaccination. So this is not really explicitly about race. This is around South African news around vaccination. And so what Nnaemeka did is he created a white versus black dimension, and subtract the one from each other. Now you've got a sort of a race dimension, race bias within the embedding. And then we can ask ourselves, well, how close, what's the cosine angle, the cosine similarity? You can see there, what's the cosine similarity between all these other words and the race dimension? And we can see it's remarkable. These words over here were generated, some of them by ChatGPT, others from other research on race stereotypes in South Africa, etc. So these are stereotyped words, and the blue ones are stereotyped black, and the white ones are stereotyped white, like taxpayers, ambitious, wealthy are white stereotypes, and township, Soweto, and HRV are black stereotypes. And we can see very clearly that this dimension that we identify within the embedding is very strongly associated or differentiating the black and white stereotype concepts or words. So And this is even in a body of text which is not explicitly about race nor about stereotypes. So we can see how these biases, the way we talk, we express and we use and we these biases, whether they're conscious or unconscious, and they are picked up and absorbed by these word embedding models. And now we have some basic technology to study them and represent them. Okay, so what I've been trying to explain or describe in this presentation is, and I've got a picture of it there, a three-dimensional sphere. Just imagine it's 250 dimensions or 500 dimensions or even 1,000,000 dimensions. It's a very, very complex object. And inside this sphere is all of our language. It's on the surface of the sphere, all the words that we use. And their place, each word's place on the surface of the sphere depends on how we've used the word. In other words, how do we treat it? The same as those pictures I showed you earlier on of lawyer and flight attendant and Asian girls. It's how do humans treat objects, concepts, etc. So what the word embedding model do in a very, very simple text recognition task, it just reads all the language and tries to guess the next word. It absorbs these biases. And so we have an incredibly magnificent object here, this word embedding. And as some of the questions have already alluded to, this is a very, very simple algorithm, and it's a very, very simple word embedding, giving each word a single representation. The word embeddings or the models that are involved in ChatGPT and other large language models are infinitely more complex than this. But there's an important feature of these models that I want to try and demonstrate now, and that is that all these biases are related to each other. So a bias is fully connected in language. This is actually why they are unable to debias algorithms. You can't just like sort of work out what the gender bias is and then sort of go and extract, like sort of partial out, to use our language, to partial out all the gender bias and then leave a non-gendered or non-racist embedding model there. It's impossible because every single bias is ratcheted up by every other bias. All these biases are interconnected. And how do we know this? Is from the analogy test that was reported first by Miklov and colleagues, the folks from Google that developed this word embedding in 2013 in the first place, the word to vec embedding, this model. And basically what they showed is that these word embedding models can solve analogy tasks. You can ask it, a man is to woman as king is to, and it's going to tell you that man is to woman as king is to queen. And how does it do that? It solves the problem in the geometry of the word embedding. So it shows that the differences between man and woman are somehow related to these differences between king and queen, which would also be somehow related to differences between flower and insect, or between some of the studies have shown the gendered representation of foods like salad and steak. All these concepts are related to each other. So how does it work? Basically, what Miklov and them showed, if you take this is man minus woman, you know this first little bit over here, you're basically doing some vector mathematics. King plus woman minus man is equal to queen. That's the gender math behind it. But conceptually, in terms of what we've been discussing over here, woman minus man, you remember you've got the woman dimension over there and the female bias, the male bias, you subtract one from the other, you've got a direction in an embedding. So basically what this says, you start at the word king, you take one step in the direction from man to woman, and it's going to take you to the word queen. So the whole architecture of these embeddings is governed by these biases. I don't know if that's a clear way of expressing it. So I've explained you start at king, move one step in the direction of the gender dimension towards woman, and you end up at queen. But basically what this is showing us is that these biases, different concepts, biases are related to each other in this embedding. So in other words, all our biases are actually related to each other in the language that we use. There are these implicit associations between word meanings in the way we use the words, and these models absorb them all. Okay, so a little bit to the work that we're actually doing now on this. So our application is, so the particular application we want now is to create, I've just shown you how you can go between man and woman and king and queen. What we're trying to do is now we want to bridge between words, vaccination related words like hashtags, for example, and people who use the language. So we're trying to bridge between attitudes and people. There's a structural, relational structure between words. They're all related to each other in terms of biases. And there's a community of people over here, and they all relate to each other in terms of the words that they use. And so we've got this two-dimensional structure. On the one dimension, we've got words, attitudes, discourse, language. And the other dimension, we've got human beings, groups, associations, relationships. And of course, these two things are related to each other. They emerge around each other. For example, the concept of an opinion-based group. It's the kinds of opinions that we use to show the identities that we want to portray. Helps us know who we and who others are. And this is especially where this technology is useful. It's helpful for us to actually investigate this reciprocal way in which attitudes form in communities and communities form around attitudes or words or language. So essentially what we do over here is we create something called the user embedding. We call them speaker landscapes. So we're using tweets over here. So we put the agents, in other words, who used the language? Whose tweet is it? So we put the tweeter in the context of their tweet. And then not only on top here, we've got a word embedding, which is a three-dimensional representation of how close and far words are from each other. But now we've got the people. So in other words, not only in this discourse over here is no to vaccine and kill by close to each other. In other words, they're almost synonymous to each other in this anti-vax discourse. But we can see that they're also close to QAnon. So QAnon is using that kind of language, very far away from Bill Gates, for example, who's on the other extreme, close to program and booster and vaccines work for all, similar to the World Health Organization, the Ministry of Health. This is, by the way, this is not real data. It's just toy data to demonstrate the point. But what we're basically studying over here is the embedding not only of words and concepts each other, but also the community of people in that same language. And this here allows us to break free from Likert scaling, semantic differential, to a different way of representing the distribution of opinion in society in the naturalistic way, and by the language that they use, the concepts that they are sharing. And it's incredible, actually, from the work that we've done. I've just got a few minutes left. From the work that we've done, that it's able to capture group differentiation and opinion so well, given the fact that, you know, if you're speaking the English language, for example, and a lot of this work on the internet and these word embedding models is based in English, although there are very successful models based on agglutinative languages like Turkish as well. So basically what we can do now is we can study individual differences in opinions. We can see how individuals are distributed through these what we call speaker landscapes. We can do a qualitative analysis so you can see what are the concepts that are associated with these different groupings, and we can really study the sort of the ideological structure of our society. And here is just a quick thing of how well does this work. You know, is it a good way of representing individuals? And so this is a test of that. Actually, this paper is now published. It's an old slide. It's was published in 2024, this paper. So what we do is we take all the individuals and we make two aliases for each individual. we just randomly assign their tweets. So say all my tweets over here is randomly assigned to Kevin 1 and Kevin 2, and we do that for everyone. And then we sort of just correlate how close are Kevin 1 and Kevin 2 embedded in the embedding. So in other words, if you just randomly assign your tweets in two groups, are the two random sets measuring the same Kevin? And the answer is, if you've got enough words. If you've got 50 closest words, it's almost 100% accurate in the exact same place. But I mean, it's very reliable. So there we are. It measures individual differences very reliably. So there's the one take home. And here is an example. This was published recently in the journal Political Psychology. This is analysis of a US vaccination debate where the red dots are Republicans, the blue dots are Democrats, the yellow dots are public health discourse, public health agents, and then the black dots are anti-vaxxers. And what this analysis showed in a remarkable way was how during the course of the pandemic, the Democrats borrowed the language of the public health folks, and the Republicans borrowed the language of anti-vaxxers, and they managed to separate themselves into these polarized communities by borrowing this language. They weren't they prior to the even though there was debate around vaccination, they weren't nearly well organized like this politically before the COVID pandemic. And it's amazing how clear this is. If you can even see this, the language models basically. This one little section over here, it's got like flu vaccine injury, learn the risk, etc. We can almost call these vaccine hesitant folks. And right at the end here, like right at the polarized end, you've got sort of Bill Gates vaccines kill. You've got the real anti-vaxxers there. So these models are very, very powerful ways of identifying what we call opinion-based groups or small groupings of people that are aligned in terms of the language that they use. There's much, much more else that I've learned and I can say about what this teaches us about us. How do we give opinions? But I'm out of time for this presentation. I'll take some questions and some comments, and perhaps at the end, after Nnaemeka showed us how to do this, we can have some more discussion. Thank you very much.
Thank you so much, Kevin. We do have a couple of questions if you so one question was, not sure if I missed this point, but is there a specific software program that you use to handle these data analyses?
Yeah, we don't have a specific software program. This is Nnaemeka is going to show you how he does it. He's using Python code, and we've got a GitHub repository where you can access the code. So yeah.
Awesome. Does it only work with two categories? Is it possible to apply it with more than two category bias, like with 4 or 5 ethnic groups or with multiple genders?
Yes, you would be able to do that. You'd have to think of it's going to always make these comparisons between two, but you can have multiple comparisons.
And I will leave the remaining question for after Nnaemeka's because I think we might actually have that answered then. Thanks so much, Kevin.
Okay, thank you. And I'll hand over to Nnaemeka now.
All right, over to you, Nnaemeka. Thank you.
Okay, good day everyone. Thank you, Kevin, for the more conceptual overview of how to use embeddings to study bias. So for this part of the workshop, what I'd specifically be doing would be to do a more practical demonstration of how to apply these embeddings, specifically the speaker landscape that Kevin demonstrated at the end of his presentation, to studying socio-political issues, for example, bias, right, and polarization, right? And for the specific use case, right, I'll be showing you how to use these embeddings to create a speaker landscape for detecting identity bias in the news selection and representation of quotes, right? And there are going to be three parts to this demonstration, right? The first part would involve the pre-processing of the data, which is a very important step to the data analysis. And then the second part would be the training of the model using the pre-processed data. And then the last part is where you start to construct your speaker landscape, right? For looking at the convergence of speakers based on language use. But before I get into this, I wanted to share the GitHub link that contains the code for training some of these embeddings. I'll put that in the chat now. And I should mention that what you'd see in the GitHub link might differ to an extent to what I'd be showing you. But essentially it's the same thing. I'll put the GitHub link in the chat now. Okay, I've put that in the chat. So okay, let me get back to okay. So the first step in training some of these embedding models is your pre-processing and data cleaning. There's this common saying in data science that you get what you give your models, right? So for example, you train your models with garbage data, you get garbage in return. And that is why pre-processing and data cleaning are very important steps in training every model, not just specifically to embedding models. Right. So the first step in pre-processing your data involves loading all of the libraries or packages that you need. I'm not going to run the codes because some of them do take a lot of time to run, and we don't really have that much time. But what I'll be doing would be to show you the output of the codes that I did run earlier. So the first step would be to load all of your packages, and the most important package you need here for the pre-processing is the Genzim package, right? And specifically why you need this is for creating your bigrams and n-grams, right? So these are connecting your English words that are core in your text corpus at least 30 times. That was the specification for this very use case, right? So once you've loaded your packages, the next step would be to mount your Google Drive. You can skip this step if you're running Python on your machine, right? But I like to run on Collab, which allows me, because it allows me to use Google's computational capacity, right? But if you're running on your machine, you can skip the stage here, but you'd have to specify on your, on the Python software on your machine where the data is on your computer or machine, right? So once you've mounted your Google Drive, the next step would be to specify where in your Google Drive, you specify to Collab where your Google Drive the data is located, right? So this is the specification, right? And once you've specified this, the next step would be to load the data from that path, the specified path onto your Collab environment. So once you've loaded the data, you can do some simple descriptive statistics. So here I wanted to see the unique number of speakers, right, in the data set. And like I said earlier, the data that I'm using is a data on the COVID-19 vaccination quotes in South African news. Is a quotes data, right? And what I'm doing with this data is to try to look at identity bias in the news selection and representation of these various quotes, right? So look at bias, identity bias by race, by gender, by affiliation, right? And I'll be showing you the results of that when I get to the third notebook. Right, so you can run some simple descriptive statistics. Here it shows you the number of unique speakers and then the data point, the number of data points, right? So we have a fairly small data here, a data set of approximately 23,000 data points, right? And Kevin did speak about fine-tuning your data, right, on pre-trained models, and I'll show you how to do that when we get to training the embedded models. So once you've loaded all of those and, once you've loaded your data and run some descriptive statistics, I also wanted to print the data here as well so that you can see what the data looks like. So this is the quotation data, the news quotation data on COVID-19 vaccination, right? And you can see the title of the news articles where those quotes were extracted from. These are the URL links to those articles. And then these are the individuals, these are the speakers. And it is with this individual that you plot your speaker landscape based on their language use. And in this sense, not essentially language use, but based on how the news selects and represents the speakers. right? So you also have their attributes, the various attributes or information of those speakers, like their gender, their race, their affiliation, right? And then you have the quotes, right? The various quotes from each of those speakers and the dates those articles were published, right? So once you've looked at all of those dynamics, you can then get to cleaning your data and pre-processing it as well. So the first step for me was to remove punctuation strings, right? I've specified the punctuation string and then also manually specified some other punctuation strings for that should be taken out of the data, right? Because you don't want to embed punctuations. They're not going to make very useful meaning for you, right? If you do embed them. But I've also specified that some punctuation strings are retained in the data. For example, the underscore sign, because this is very useful for creating your bigrams and n-grams, and I'll show you that in the next few chunks. And also specify that the and sign is retained, right? And then for further cleaning as well, I've had to define a function here for removing, for example, HTML tags, right? I wanted to remove this HTML tag from the data because it was very prevalent and created noise, right? So I removed this and only retained the and sign. And then here is our parameter for removing the punctuation, the punctuations that were specified up there. And then the last was to lowercase all of the words, right? This is a very important step as well, right? Because you want to ensure that the meaning of words are stable across your embedding models, right? You don't want, for example, the model to learn a different meaning for, or to assign a different embedding to the uppercase version of a word than the lowercase version, right? Because this sort of introduces noise, right? The uppercase and lowercase versions of words maintain the same meaning. So there's really no point assigning different embeddings or vectors to those words, right? So you lowercase all of the words, right? Just to ensure that uniformity across the different keywords, right? So once you've specified all of those, you'd have to then start to apply that function to the data itself, right? So this is where I started with the application. Of the function, I applied it to utterances and then assigned it to a new column called clean text, right? And here I've also had to, and this is specifically for the speaker names, right? The speaker names that are down here. I've had to remove the space, for example, between these two words and replaced it with the underscore sign, right? Because I wanted those three words there, those three keywords there to be joined together. That's why you remove the space and then you replace. And then I've also had to lowercase the speaker names, right? Just to ensure that uniformity as well, right? And a very important step as well, and Kevin did show this earlier too, was to prepend this agent token to each of the speaker names, right? The reason why you do this is so that when you start to train your embeddings, right, you can include these agent tokens in the training data, and then you can look at the relationship between these agent tokens and their vector, their quotes, the vector representation of their quotes, right? And also more importantly, when you start to extract those vector representation, you need a way to identify the speaker names or the tokens of those speaker names in the embedding, right? So that you can extract those vector representations of the speakers and, based on their language use, right? So that is why you prepend each of the speaker names with the agent token here, right? And then some other minor processes was also to convert the date to a format that Python would better understand, right? And then also sort the values by date. So here I wanted to print the data just to make sure that the cleaning was actually done properly, and also specifically that the punctuations were removed. And here is where you start to create your bigrams, right? The reason why you create your bigrams, like I said earlier, is so that words that co-occur can be joined together by an underscore sign, right? You don't want, for example, South African, which usually co-occur, right, and holds a more stable meaning, to be embedded differently, right? So you don't want South to have a different embedding and then Africa to have this different embedding, right? Because that creates noise when these two words hold meaning together, right? So you assign, you create your bigrams for this main reason. So the specification here was to go through each of the sentences and then find words that co-occur 30 or more times and then join them together with an underscore sign, right? So South African would be joined together with an underscore sign. And that's why you create your bigrams. And as part of this process as well, I've had to create bigrams of bigrams, that is n-grams, right? So the reason why you do this is, I'll give an example with South African as well. So once South African has been joined together using that underscore sign, right? There might also be other words that might be very meaningful to South Africa, so to South African rather. So for example, South African government, right? These three words hold meaning together and you don't want them to be embedded differently. So the reason why you create your bigrams of bigrams or n-grams is so that you can better detect those words that co-occur 30 or more times with South African, for example, and then join them together by using an underscore sign, right? So once you create these bigrams of bigrams, you have those kind of patterns, right? So that is why you create your bigrams, and that's essentially what I've done here. And the specification was to create, join words with 30 or more words together. And the vocabulary size there was to make sure that you don't overload the RAM, right? Because what you don't want is to overload your RAM with all of the data at once, and then your memory crashes and you have to start the process all over, right? So the sentence generator helps manage your RAM efficiently so that everything don't get overloaded at once. And the English connector words there is to make sure that stop words like at, to, do not, obstruct the construction of phrases, right? So that is why and how you create your bigrams. And this is a very important step, right? If your embeddings are going to reliably learn the association between words and between or among words, if you will, right? So that is the final part for the pre-processing. And here I wanted to print the pre-processed data just to make sure that everything looks okay. These are the speaker names, and then this is the down here, you can find the n-grams, the bigrams of bigrams, right? So for example, you can see a good example here of Pfizer vaccine has been joined together as a bigram, right? Because they co-occur 30 or more times, right? And here, this last step, which I've commented, was for saving the data, the clean data as a TXT file for your training, right? And I've saved that TXT file because it's easier for embeddings, or these embedding models to understand the when you've put the data into a TXT file. So specifically the columns that I've extracted here are the speaker names, right? The clean speaker names with the agent token prepended to each name. And then the clean data, especially this last part with the n-grams or bigrams of bigrams. So what you have is a TXT file with the speaker names, sorry, the TXT file with the speaker names, and then there are quotes on the other side, right? So that is how you create why you pre-process and clean your data set, right? So the next part, or the next notebook rather, involves essentially training your embedding models, right? And with the previous one, the first step would be to load your various packages, right? And the most important package here as well, especially for training your embedding models, right, is the Genzim package. There's Genzim Watervec package, right? And I'll speak about the model specification down the line. And with the previous one, you also have to mount your Google Drive as well, right? This can be a pain, especially when you have to do it consistently, but it is the price you pay for using Google's computational capacity. So you mount your Google Drive to specify to collab where in your drive the data is located. And then you also specify your model seed. The reason why you specify your seed is to ensure reproducibility of your results and training, and also to minimize randomness in the whole training process. And you specify your print loss function as well, right? Why you do this is what the print loss function does is it helps you monitor the convergence behavior of the model, right, between epochs, right? So when the model decreases between two epochs, that would be a sign that the model still has a long way to learn, or to train, right? But if the decrease between two epochs is minimal, that would be a sign that the model is actually nearing convergence, right? That is to say that the model has been learning or is learning something meaningful from the data, right? So that is why you specify your print loss function there. Here is your data generator, right? And data generator is essentially a model is an iterator, right? Is a class iterator, right? It goes through the data and then helps you manage it's a custom iterator rather. It goes through the data and helps you manage the data specification, how much data is being plugged into the training, right? Like I said earlier, you don't want to plug all your data into the model and then you overload your RAM and crash it, and then your training has to start over, right? So data generator helps you manage that process, right? And the specification here, this path to data lets it know where in Google Drive or on your machine the data is located. This share data is a parameter for letting it know whether you want to train your models with all of the data or a part of the data or a section of the data, right? So the specification I've given it here, this 1.0 is for it to train with all of the data, right? But if you wanted to, for example, bootstrap your results, right, you would specify here that the model uses, the specification would be 0.5, right, for the model to use half of the data, right? And then chunk size here is also very useful in letting the model know how many lines the random buffer should return before it fills up again, right? And if you were to use a larger chunk size, right, your training would be faster, but that would decrease the randomness. Whereas the random buffer here lets the model know the number of lines to keep in the RAM at once before random sampling, right? When if you were to include higher values to these, it would let the RAM to know when how much data to sample for the analysis, right? Whereas a value equal to the number of all samples would lead to a more perfectly aligned random sample. And then your data seed is essentially the seed that you define earlier, right? It helps to ensure reproducibility of your training and also to minimize randomness in the whole training process. So essentially, this part is a, like I said earlier, is a custom iterator. What it essentially does is to help your help you manage how much data goes into the training, right? So that your memory and your RAM capacity is better managed, right? Especially if you have a machine or you're using a system that doesn't have very large RAM capacity to handle the processes. So once you've specified all of those, right, this is where you start to do your training proper, right? This, like Kevin mentioned, we used Watervec because of simplicity. Whereas if you were to use, for example, more contextual embedding like that, you might get different results. But Watervec it performs well, right, when you want to do something as simple as creating the speaker landscape, right, based on language use of speakers, right? So what I've done here is I've pre-trained the model because of the relatively small size of the data, the potential data that I'm using for this very process. I've had to pre-train the model and then continue the training or fine-tune the model, right? So for the pre-training, I had to use all of the not COVID-19, all of the vaccination utterances, including COVID-19, rabies, vaccination utterances or quotations, right? I've had to train it with that broader data, right? And the model specification here, like I said, uses Watervec, and you also have to specify to data generator where in your Google Drive the data is, the vaccination data is, right? And then you plug, Google data generator plugs that data into sentences, right, for the training, right? And data generator, like I said earlier, essentially helps you manage the data so that it doesn't overrun, the training doesn't overload your RAM. And the vector size here is essentially the dimensionality of the vector. So specifically, it lets it know how many dimensions each word should have, right? And Kevin did explain the dimensionality of vectors earlier. So the specification there is for each word to be trained as a 250 length vector, right? Usually the specification is from 100 to 300, right? And anything beyond 300 is usually tends to result in problems and more noise in the training, right? So it's often recommended to specify between 100 and 300. So window here is your context window, right? It lets the model know how many words before and after a target word should be considered a context, right? So the specification there is for you to use 10, 10 words before and 10 words after a specific word as context. Whereas SG equals 1 is essentially for the model to use the skip gram algorithm. And why you use skip gram works better on smaller data sets than, for example, continuous bag of words, right? So for the very purpose here, the quotations data we're using is a relatively small data, so we've had to use skipgram. And then workers tells you the number of thread to use, number of CPU thread to use for the analysis, right? If you have a higher thread, your training speed would be faster, but that would also depend on the capacity of your machine. And minimum count here is also a very important specification, right? What it does, it tells the model the minimum count of words, how many words, the minimum number of words that should be included into the training. That may not be a very good way to phrase it, but what it does is it tells the model the minimum number of, or the minimum frequency of words, right, that should be included in the model, right? So if, for example, you have a larger data set of, say, 3 million to 10 million news articles, right? The minimum number or the minimum count there would be higher, right? So, because if you have a higher minimum count, right, that would enhance the reliability of your embedding, whereas lower often creates noise. But because of the relatively small size of the data we're using for the training, I've had to specify one there, right, just to make sure that every word gets a chance or gets into the training, right? Whereas the sorted vocab tells the model to sort the vocabulary frequency in a descending order. And then seed there is simply the model seed, right, which is very important for the reproducibility of your results, right? And epochs essentially is the number of times the training process goes all over the data, right? So I've specified 30 epochs, right? And with each epoch, there's a print loss, there's a loss function there to print the loss in each epoch, right? And like I said earlier, what print loss does is it helps you monitor the convergence behavior of the model, right? If there's a significant decline or decrease between the loss in two epochs, right? That would be sign that the model is still in the process of learning. Whereas if the decline or decrease is minimal, it would signal that the model is almost nearing convergence, right? So this is what the output looks like. And I'd like to demonstrate this print loss function between these two epochs, right? So you see here that there's a significant decline or decrease between the approximately 1.4 million here and the 961,000 here, right, which is a significant decrease, right? Whereas here, right, you can see that there's a minimal is less decrease between these two epochs. So overall, what you want is to see that there's a general trend of decrease across these epochs. So you can see that it started very highly here and then very low, not very low, but yeah, fairly low here, right? So essentially, you want a pattern of decrease between these epochs, right? So that is how you train your embedding model. It takes, the time that it takes to train these models depend on the size of your data, right? If you have a larger data size, it might take more time to train them, whereas if it's smaller, right, it takes less time. So you pre-train and then you continue with your training. You fine-tune the model on the pre-trained, specifically for my use case, right? You fine-tune the model, essentially continuing the training. So this is a form of transfer learning, right? You train on the larger data set and then you adjust the smaller data set to learn from the context of the larger data set, right? That is why you fine-tune, and that's essentially what fine-tuning does rather. So here you also I had to specify the data generator as well because of the fine-tuning, but essentially the parameters are more or less the same as the ones up there. And yeah, for the fine-tuning as well, you have to specify to the embedding model where exactly in your Google Drive the pre-trained model is located, right? And one thing that I missed up there as well, you have to save your models to Google Drive. I've had to comment this because I don't want it to save any random file to when I do run it. Right, I don't want it to save any random file to this, but you save your embedding model and because you're pre-training, you don't normalize the vector or the model to unit length, right? Because once you normalize, you cannot continue training. But here you can normalize, right? Because this is where training continues. And yeah, like I said earlier, you specify to the model where exactly in your Google Drive the the train model is, and then you continue training with you fine tune rather with the more specific COVID-19 vaccination data set. And once you've completed the training, you can then go ahead to normalize your word vectors, right? And once you've normalized and saved your word vectors, this is where you save. You have to save the embedding again. Once you've normalized and saved, right, you can then go ahead to plot your speaker landscape. That is the landscape that Kevin showed earlier. And this is also the print loss function for this very training. So the last step or the last part for the analysis is where you actually start to create your speaker landscape. And with the previous one, you run your packages again. And the most important one for me here is the dimensionality reduction technique, right, which is UMAP. So all of those very large vectors of 250 or more length, right, you have to reduce them to 2 dimensions. And Kevin did show that earlier, to create your speaker landscape, right, which looks at how speakers converge or cluster based on their language use. And in this sense, I'm looking at how the news draw them into specific news areas or topics, right? And then here you also have to load your Google Drive. You have to mount your Google Drive rather. And once you've mounted this, you specify the location of the trained embedding on Google Drive to collab, right? And you assign it to this object embedding. I've assigned to this object embedding, and then I've printed the embedding object, right? You can see the vector size of 250 and then the number of keys or the number of word vectors that have been trained in your that have been used in your models, right? So I have approximately 27,000 keyed vectors in this embedding model. And once you've loaded the embedding, the next step then would be to start to aggregate the speakers by their quotes, and then also get the speakers with 5 or more quotes and then extract their vector representations, right? So the first step for me was to get the speakers with 5 or more quotes. And the reason why you do this is to ensure the reliability of the speaker landscape, right? So you don't want, for example, a speaker with 1 quote included in the landscape, because that might create noise and make it difficult to detect any patterns and trends, right? So once you've included your speakers with 5 or more quotes, the next step then was to aggregate the speakers. So you aggregate all quotes rather by speaker, by each speaker, right? So that each quote from each speaker is assigned to 1 speaker, right? And then once you've done this, you can then go into the embeddings and get the embedding of vector representation of each speaker using the assigned embeddings, right? So these are the various steps that are important for doing that. And this specifically is where I got the speakers with 5 or more quotes. And then this is where I got the vector representation of the speakers from the stored or the objects embedded up there. And then after I was done, I wanted to print the data frame just to see what it looks like. So this is what your speaker landscape data should look like. You have your authors, which are the speakers, right? And the filtering process, that I mentioned earlier, 5 or more speakers, speakers with 5 or more quotes rather, resulted in an aggregate number of speakers of 503, right, compared to the 8,477 speakers that were in the original data, right? But that is the cost you pay or the price you pay to have a more reliable embedding. You have to drop some speakers that you don't think would be very meaningful for your speaker landscape or detecting patterns in your speaker landscape. So at the end of the day, we have 503 speakers, and I'll show you the speaker landscape of the speaker landscape plotted with these various speakers rather. And these are the quotes, right? The quotes from those speakers, the aggregate quote from those speakers. And then these are the vector representation of those speakers, right? These are the vector representations that we would be reducing to 2 dimensions using UMAP, right? And that brings me to the dimensionality reduction of these vectors, right? So for doing that, we use UMAP. And you start by assigning your UMAP seed to ensure reproducibility of your results, right? And once you've assigned your seed, you can then start by, depending on how many dimensions you want, right? So for speaker landscape, it is often best to create one with 2 dimensions, right? Some people might want to create 3 dimensions, even 1 dimensions, right? But it is depending on your use case, right? So here's the specification or the parameter for reducing the vector to 2 dimensions, all of those vectors to 2 dimensions, right? And then once you've done that, I've assigned it to this object, right? I've assigned it to this column rather in the data frame called this. And I've also had to differentiate those vectors, right? Those two-dimension vectors, because I wanted to do some other analysis looking at the cluster quality of those different embeddings, right? But the most important part is the two-dimension reduction of those speakers, right? And once you're done, you also I always like to save, right? Just so that the data is somewhere in my Google Drive. So here I saved the output of that. And yeah, this is what your speaker landscape or vector representation of those speakers should look like. So you can see the aggregate vector representation of the speakers here. These are each of the speakers. These are their quotes, and these are their aggregate vector representation. And this is the dimension, the two-dimension vector, right? And this is the X and Y that I showed you earlier that I wanted to use for some other use cases. So once you have that speaker landscape, the next step is to get the information or the attributes of those speakers, right? And you need those informational attributes to plot your speaker landscape. And the information here includes information like race and gender, right? And to do this, I had to load the speaker landscape data. That is this data that I showed you here, and then the information data of each of those speakers. And then I merged those two data sets, right? And then saved it to Google Drive as well, just so that I have the data there, right? So once I merged by the author names, by the way, I should mention that. And once you've saved, this is the last part to the data wrangling, if you will, right, before you start to plot your speaker landscape, right? So here I've loaded the merge data again, and then printed the data set so that you can see what it looks like. So this is the overall data of the 530 speakers. These are the speaker names, and then these are all of their quotes aggregated. And then this is the vector representation of the speakers. And then this is the two-dimension, the vector representation reduced rather to two dimensions, right? And then down here, you also have the attributes of the speakers, their affiliation, their gender, their race, depending on whatever attributes, right? So with this data, you can start to plot your speaker landscape. And this is where I started with that plotting. So for the plotting, I used both Seaborn and Matplot, right? Matplot specified the specifically here, figure size, and Seaborn was actually the very package that I used for plotting the scatter plot here, the speaker landscape. So this is essentially your speaker landscape, and each dot here represents each of the speakers based on their language use, which is similar to the dots that Kevin showed earlier. But in this case, I'm applying it to looking at how the speakers converge based on their racial groupings, or rather how the news draw the speakers into various thematic areas, and how that results to the convergence behavior that we are seeing here. So you can also see some interesting patterns here. You can see that white international speakers are very quite clustered down here, and Black South African speakers are quite clustered here, and these are the Black international speakers. And you can see that white South African speakers are quite dispersed across the landscape. And with this, you can start to see some bias, right? You can't see the bias until you start to actually look at what they are discussing on, and that tells you what news areas what areas in the news that journalists and South African news draw them into, right? And so this is essentially a speaker landscape, right? What I wanted to do here was this is a measure of cluster quality using silhouette scores from this very library here. So what I wanted to do here was to look at the cluster quality of these different speakers, right? And you can do that using silhouette scores. So silhouette scores ranges from -1 to 1. And groups that are approaching 1 are more cohesive than those approaching -1 or even 0. And those approaching -1 are more dispersed, right? So this is our measure of cluster quality. And you can see from this density plot here that Black international speakers and Black international and white international speakers are closer to 1, which tells you that they are more cohesive compared to, for example, white South African speakers that are more dispersed across the landscape. So you can also see that pattern from here. And Here, I wanted to show you how to analyze content in speaker landscape, right? What I've used here is topic modeling, which some of you may already be very familiar with. So what I did was I ran topic modeling in R, right, using STM topic modeling, and then I got those keywords from R and assigned labels to them. There are essentially 11 topics here. I assigned those labels to them, and then I picked up those keywords, located them in the embedding, right? The training, the embeddings that we trained earlier. I located those keywords in the embedding, calculated the average or the mean or the centroid of those various keywords for each of the topics, right? I calculated the centroid of each of those keywords for each of the topic and then looked at the cosine similarity between the speakers, those 503 speakers based on their grouping, right? So for example, the racial grouping here, I looked at the relationship between those speakers in each group to the centroid of each of the topics, right? So this gives you this result here, this result down here. So this box plot here essentially looks at how groups are converged around various topics, right? And the interquartile range here tells you, and they are all measures of variability, right? The interquartile range, the outliers and the whiskers of each of the boxes, right? They are measures of variability, right? So from this, you can see how converged various groups are around various topics, right? So for example, from this, you can see and also begin to see some identity bias in the new selection and representation of these various speakers, right? So for example, here you can see that between South African speakers, white South African speakers are more drawn into more global type of vaccination topics. And then between international speakers as well, white international speakers are more drawn into more globalized type of topics, right? Compared to, for example, Black South African speakers that are more drawn into South African type of topics or South African related topics, for example, school staff vaccination in South Africa, mandatory vaccination for workers and students, and SA government procurement, right? These are South African specific topics, right? And I had argued in the paper that I wrote based on this analysis that this perpetuates the epistemic line, right? Which is a remnant of coloniality that continues to determine how knowledge and authority are divided, with Eurocentric or Western knowledge often equated with universality and African knowledge particularity. And you can see that universalization and particularization of knowledge here, represented here. And more importantly, you can also see how these various groups, for example, you can see more specifically how white speakers are drawn into more technical type of vaccination debates. So for example, these are the white speakers, and you can see that they dominate the topic on COVID-19 variants and public health risk, which is a very technical topic, and then vaccine trials and safety as well. Right, you can see that white speakers dominate those topics than black speakers. So with this speaker landscape, right, and specifically applying this kind of content analysis to speaker landscape, you can start to see some patterns in identity bias, right, when it comes to race, for example. It tells you who the news gives a voice and where, right? And you can detect that using speaker landscape. So it shows you the uncanny capabilities of these techniques, right? It can help you detect bias even in uncharted areas rather, like the new selection and representation of quotes, right? So I also plotted the speaker landscape by gender. You can see that there seems to be a healthy mix, right, across how those speakers are sectioned by gender. But when you start to look at the density plot here, you can start to see some biases, right? You can see that male speakers dominate than female speakers, right? And then I also did some content analysis of the speaker landscape. You don't see much more patterns here compared to race, right? But you can also see that, male speakers tend to dominate most of the topics, 6 out of 11 topics, than female speakers. So this is essentially how you can use speaker landscape to looking at who the news gives a voice and where, and more importantly, looking at the news and journalistic selection and representation of quotes, right? And it can also be applied to different areas, right? It goes beyond identity bias, right? And Kevin showed how this can be applied to looking at the vaccination discourse in social media, right? With this, you can start to see the patterns of convergence of pro-vax and anti-vax, right? And the news as well, right? And within the People Opinion Networks group at the University of Johannesburg, we developed this technique and applied it to looking at the vaccination debate in South Africa. And then also used the machine learning classifier to classify pro-vax and anti-vax, and then looked at the patterns of convergence or clustering, right, in that Twitter data. So with that, you can start to see how groups converge based on structure instead of logic, which points largely to social inertia. So yeah, this is how you can apply speaker landscape, and I'd be very happy to take questions and comments. Thank you.
Thank you so much, Nnaemeka. So we have quite a few questions. I'll start with one question on your demonstration was in Python. Can we also do this in R? I know you used you looked at some modeling and you did some modeling in R, but can you do the whole thing in R, or do you have to use Python?
I mean, most of the packages and libraries that are designed for running the speaker landscape, I'm not sure whether they have, because I've never really tried using them in R, but most of the packages like the Genzim package that you need to train your embeddings, they are largely Python-based packages. So I'm not sure, but maybe there are packages that are out there to use them in R.
Okay,
I can
thank
come
you.
in there. So yes, there are packages that can do the parallel analysis in R. It's just that our our pipelines are written in Python, so it would be easier for someone to starting out to just use our pipelines and adapt them. To be very easy using also ChatGPT to tweak the pipelines or even to convert them into R. That's where these large language models also have a great application.
Right. Okay, great. And what's the minimal data we need for this? Is it just the tweets and the names of the tweet authors? Is it, I guess they're talking about the social media landscape data set. So
So
I guess the question there is, what metadata, aside from the actual language and the identity of the speaker, do you need, and where do you get it?
yeah, I mean, the main ones that you need are the speaker names, right? The identifier for the speaker names, and then the other data, for example, the quotes data or the speech data, if you're looking at social media data. Those are the main data that you need, right? And this has also been applied to Reddit as well, right? Looking at how various speakers on Reddit converge based on their language use, right? Gender, parents by gender, right, converge based on their languages. So those are the key data sets that you need, the speaker data and the speech data or the quotes data of those various speakers. With that, you can then start to construct your speaker landscape.
Uh-huh. Okay, so a question for you, Kevin. You said that earlier that to calculate bias, you calculate the average of all female words and all male words. How do we know what all female or male words are? Are there lexica for that?
So that's actually what one of the problems that Nnaemeka is working on at the moment. Exactly that, like which words do you choose? And so it's quite easy with gender because there's lots of parallel words that are very central, like sort of mom, dad, him, her, uncle, aunt. So it's a very standard way in which gender has been measured in with those words over and over in many different studies. With the race, it's very tricky, and that's what Nnaemeka's PhD works on. But there are metrics like parallelism. It's like similar to what we call a Cronbrook alpha. Like the internal consistency. There parallel concepts in word embeddings to help us make those decisions. Yeah.
Okay, great. Jasmine, you had a question. Would you like to come on?
Hi, sorry. When I raised my hand, that was an accident. I was just trying to give a react. But thank you so much. This has been super helpful. And I wondered if it would be okay if I had some follow-up questions to send an email to either of you at some point, as I'm very interested in this method.
Yeah, absolutely. We are very keen on, we think it's a fantastic method and are very keen on people using it. It's there's just so much work. As I said earlier, I'm just like starting with the analysis. You know, those plots that Nnaemeka showed of the way into which those clusters are separated. From my understanding at the moment, that there is, it's got a parallel. It's almost representing our cognition. Like if you're going to speak it, if you're going to make an opinion or express an opinion about COVID or about whatever, you want to know who your audience is. And how do we know who our audience is? It's from the language that they're using. And these models are actually representing how clear people are distinct in their groups. So they're modeling something about the way in which we engage in social communities. Yeah, and there's stacks of work to still be done in this. So we'd be very happy to work with whoever wants to pick up these methods.
Thank you. Celestine, would you like to ask your question in directly, or should I? Okay, I'll just add you to the screen. There you go. Okay, so the question was, where are you? Could you say more about the data? So there's quotes from news articles, but how are you extracting these and attributing speakers to them? She's wondering if this is within some XML or JSON.
Oh, yeah, I can talk about that. So the data that we're using, I think, fortunately enough, we got the data from this organization called Media Monitoring Africa. They did the quotes extraction. They had a specific instruction for extracting quotes from the data itself, from the news articles, right? So they extracted the data from those quotes, and then they assigned the attributes of those speakers, right? I think it was largely a human assignment or evaluation of the speakers and then assigning each of those attributes to those speakers, right? So they assigned, they extracted the quotes and then assigned each of those attributes to the speakers, right? And we got the data, right? And that meant that, you know, there are so many possibilities for us to use this data for analyzing patterns and trends in, you know, in how groups speak together and how the news specifically draws them into various type of news areas and topics. So to answer that, we got the data from Media Monitoring Africa. They did the extraction and assigned each of those attributes to the speakers, and then we use the data for the analysis.
Thank you. Max is asking, what if you only have the 20,000 words you mentioned earlier? On what do you pre-train your model then? Are there already pre-trained models available?
Okay, perhaps I can respond there. So the analysis that we've done had the least words was the South African debate on land. So it was we had, I forget how many. We had thousands of quotes from 10 years of South African media, and basically those quotes were hand coded by that company, as Nnaemeka was explaining. What we are trying to do now is we're trying to build a quote extraction model. There is some other colleagues that built a quote bank of international news, but we want to try and build a quote extraction model to develop contextualized quotes out of the South African data, Southern African media data. So it's the universe of it. So if we've got good quality quote data, then we'll be able to run outstanding models of like sort of the public debate and who's positioned in that public debate and how that public debate has happened. And these new models will help us develop and extract those quotes. But anyhow, to get back to the point here, we had 3,000 quotes on land, which is very, very little. And there were 100 and I think about 110 South African politicians who were represented in those quotes. And we created a very reliable and informative model by pre-training the data on all the quotes, which was, I think, about 50,000. and then post-training it on just the 3,000. So you don't need lots and lots of data, but I mean, 50,000 quotes is quite a lot of data. But you do need substantial data. Of course, there are off-the-shelf models, and most of the analysis in social psychology is done with pre-trained models. So we're training our own embedding models on our own data, and I think that's very important because the other models come from these big US databases like Wikipedia. It's got some of this Google News, this Google Books. So it's dominated by global north discourse. Of course, if you're going to do work in the global south and your starting point is all the norms and biases that you're getting from the global north, it's going to affect your analysis. So I really think that's important that we actually training our own models in our own context, rather using smaller data sets. These models are very, very good at absorbing biases, even with relatively small data sets.
Thank you so much. We have a question about how to navigate ethics in getting data online from tweets and comments and posts on forums and things like that.
You want me to tackle that, Nnaemeka? I can have a go at that. So we've got our data from two sources from Google, not from Google, from Twitter before Elon Musk stopped access to the API, and from the South African media data. So the South African media data quotes, we treat those two differently because the South African media data are public figures that are making quotes in the media. It's publicly available. So we have published, for example, a map, a speaker landscape of the South African land debate with the different politicians who positioned themselves differently. You know, there's some talking about, you know, pro-capital politics and other pro-poor, and we represented that with their names, and we think that's actually important. With the Twitter data we use, everyone's anonymized, so we haven't actually. We of course we need the individuals, but we don't actually need to know who those individuals are. We never show the individual's name, so there's anonymity in reporting. I don't know if that addresses all the problems, but there are obviously issues with there's issues of access. I mean, I mean part of the problem is around the ethics of representing people's names. Part of the problem is around the ethics of all our data is owned by these big companies that's stopping us from accessing it to study how bias, racism, sexism, all the other kind of isms is working in our society. I think that's an urgent ethical issue that we need to address as well. So there's many ethical issues here.
Thank you. Meta is asking, what opportunities and risks do you foresee for these kinds of methods in moving forward in political psych?
So
might be a bit of a general question, but
yeah,
just
no,
a few thoughts.
It's a deep and important and challenging question. The opportunities, I think I just froze there. The opportunities are, I think they do give us a way of quantifying how people make sense, how individuals make sense of the social environment, the social landscape. So our traditional methods in social psychology, you have got the expert, the psychologist goes and measures everyone's opinions. Everyone's opinion is given in the private context. They filled out a questionnaire. They said, this is what I think about vaccination. And then the expert creates a representation of the distribution of those opinions in society. Whereas to be a social agent, we need to have in our own heads, we need to have an own idea of the representation of our society, our audience. We need to know who our audience is. Now, what these models do is they help us. They represent how everyone sees this world, and so they allow us to produce a completely different type of social psychology. I've just got a paper, it's gone as a review and submit. It's called Human Murmuration in the European Review of Social Psychology, which is really a complex systems theory of polarization and giving of opinions, where everything is moving and everyone's opinion is given against everyone else's. So you've got this really complex structure like a murmuration, and I think these models allow us to actually get into a form of social psychology that is complex. So in other words, where we've got the structure affecting how individuals behave and individuals' behavior affecting the structure. So we've got these complex systems, really like murmurations. And I think these models open the door to a kind of psychology that we've always wanted and been seeking for, but have methodologically not been able to achieve. The risks are obviously these tools are in the hands of the powerful, wealthy, and even more so now than previously, because they literally own the algorithms. They can shape how opinion. I mean, just if you look at what happened in the last American election, we can see how opinion is being shaped, how almost by minority influence is doing what majority influence used to do. And that is through the intelligence that these models are giving politicians. So there are massive risks out there as well.
Thank you both so much. Nnaemeka, would you like to add anything? Any thoughts?
I think Kevin covered the meat of the discussion. Thank you.
Thank you all very much. Thank you all as well to the attendees. And I just want to mention that our next session is on May 29 with Emma Thomas, who will talk to us about integrating person-centered approaches with variable-centered models in research on social change. You can see the full schedule and the get on the email listserv and look and see the recording of this session with its transcription on the archive. The links are all in the chat now. Thanks again, Kevin. Thanks again, Nnaemeka, and have a great day, everybody.
Thank you. Bye.
Thank you, Ferd, and all. Cheers.
Cheers.